This slide presents the detection range of leaks depending on the type of heat exchanger tightness test used. In other words, it shows specific testing methods and the types of leaks they can detect, as well as the extent of those leaks, so to speak.
Sergey, I'm looking at this graph and I see that the unit of measurement used here is millibars.
Yes, it's millibars per liter per second.
We can also see that helium in this analytical report shows the best results in the widest detection range, but also in a vacuum environment, meaning a gas-free environment. We also know, and we've mentioned this earlier, that helium is used at 100% concentration during leak testing of heat exchangers. In contrast, we cannot afford to use hydrogen at such concentrations. The safe concentration for hydrogen is up to 10%. Could you please comment on this chart and share your thoughts on which of these methods is actually the most accurate and how practical it is to use maximum accuracy? Or rather, which level of accuracy is realistically achievable in practice?
Okay, if we take the helium gas test in a vacuum environment, then yes, it will be the most accurate. But do we actually need that level of precision? Because even at 10 to the power of -6, water still won't pass through. Therefore, for facilities where this level of precision is critical, they can certainly use this method. For the food industry, a more effective approach, both in terms of cost savings and overall test efficiency, would be a gas-based method using hydrogen. Alternatively, helium can be used, but it is significantly more expensive. That's why I tend to favor the hydrogen test. It also offers a very high sensitivity for leak detection.
Igor, would you be so kind as to share your thoughts on this chart?
I support the previous comment. Indeed, from a theoretical standpoint, the helium test under vacuum, where negative pressure is created in the circuit being checked for leaks, is the most sensitive. However, a sensitivity level of around 10 to the -12 millibars per liter per second is typically not required in practice. If we compare all the leaks detected by the gas method with the visible holes and cracks later observed on the plates, it can be concluded that a leak detection sensitivity in the range of 10 to the power of -5 to 10 to the power of -7 millibar liter per second is generally sufficient. So yes, both helium and hydrogen tests are equally applicable.
Thank you very much. While preparing this presentation, we started thinking about the types of holes and how we usually measure them in terms of size. We wanted to share with our viewers what these defects can actually look like in real life. On the next slide, we've included images from a scientific study on the corrosion of heat exchangers made from 316 stainless steel. There's a link to the study provided below. It's publicly available online. The slide shows a series of magnified images. The one in the top left corner has the largest scale available and displays a corroded surface. You can clearly see a crack in the center, right in a small groove. The following images were taken at even higher magnification. You can observe the formation of pitting. This shows how metal, being non-homogeneous, contains various inclusions, including carbon, which can contribute to localized corrosion. And on the next slide, you can see an actual piece of a heat exchanger that has a crack. The surface has been photographed using an electron microscope to show what the damage looks like up close. When I look at this, a question naturally comes to mind. These cracks aren't perfectly round, and the holes they form don't have an ideal geometric shape either. I've also heard this from you, Igor, as well as from some service providers, that there can be cracks or microcracks with a membrane-like behavior. In other words, if pressure is applied from one side, the crack opens. But if pressure is applied from the opposite side, it closes. It's essentially a misaligned or asymmetric crack, like the one we see in the top right image on the slide. Igor, could you please comment and share your findings? What have you learned about how cracks behave? What types of cracks are there? And does their shape or size affect test results? How much do leak detection test results depend on the geometry of the cracks? Are the tests prone to errors due to this geometry?
Yes, of course. When we talk about the size of an opening, we usually refer to the theoretical diameter of a perfectly round hole through which the flow can be calculated under specific conditions of pressure, temperature, viscosity, and other relevant factors. In practice, as seen in the photographs, all these openings have irregular shapes and can actually function as a kind of valve. That means it may allow flow in one direction, but restrict it in the other. For this reason, many service providers by default recommend performing two tests, first checking for leakage from circuit A to circuit B, and then the other way around.
Have you encountered such cases?
Yes. Additionally, there are cases when these cracks are clogged with poorly rinsed product residues. Sometimes a crack may remain closed under low pressure, but when the pressure increases, say from 3 to 5 bar, it suddenly opens, causing an abrupt and intense leak. This also happens in practice. That's why situations vary, and it's wrong to assume that the holes have a regular shape. It's important to consider that they may allow flow in one direction more than the other, and their behavior can change depending on the pressure.
As I understand it, and we've also encountered such results, when we run a leak test, it seems like there is a leak, but in practice it turns out there isn't one. Plates often have a very large surface area and operate at high temperatures. That means the metal can expand. And as I understand it, when the heat exchanger is hot, it can be more leak tight. But when it cools down, it may become less tight. Sergey, have you encountered such cases or not? And I'd like to ask the same question to Igor as well.
Yes, we've had such cases. It was especially noticeable during the hydraulic test, which is conducted on a cold heat exchanger. Everything seemed fine, but once the heat exchanger was heated up during the CIP process, it started leaking.
Igor, your take?
Well, overall, I can only confirm that the behavior of a heat exchanger can vary depending on the temperature. It's hard to say exactly when it will leak more. It really depends on the specific situation.
So in fact, when we conduct leak tests, we have to keep in mind that the results reflect only the current moment. For example, let's say we're using the most sensitive method, helium testing, and it detects a very small micro leak. And we often encounter clients where, during testing, we detect a small leak, meaning there's already some preliminary defect in terms of size. From what point should we start getting concerned about the results of a tightness leak test? How should this be evaluated from the perspective of a quality manager or someone responsible for product safety? Igor, how should one interpret these reports?
Here, I can refer to the recommendation of one of the service providers who, for example, consider a hydrogen leak of around 30 parts per million to still be acceptable. However, the very fact of a leak indicates that a timely replacement of the plates should be planned. At the same time, a leak of around 100 parts per million would already be considered unacceptable.
Thank you. And as I understand it, all of this really depends on the nature of the cracks, right? Meaning what their geometry is like, whether they actually allow liquid to pass through or not. In any case, if there are any signs of leakage detected through penetrant or fluorescent testing, the plates should be replaced accordingly.
One of the suppliers even said that it doesn't matter how big the leak is or what exact value we measured. If a leak is present, it means there is a problem, and the plates need to be addressed. Some suppliers don't even try to correlate the size of the leak with the degree of wear. On the contrary, they say that the numerical value of the leak might seem quite high, but upon disassembly, it turns out that the crack is barely noticeable.
Thank you for your answers.